Assalamualaikum dan salam sejahtera. So now we are moving to the second part of soil compaction lecture. Okay, we continue with the discussions on laboratory testing. Okay, with regards to soil compaction. So this is the apparatus that we use to compact the soil at lab. So for laboratory testing, we have two types of proto test, which are standard proto and also modified proto. So based on the standard, okay, there's a two standard, okay, with regards to one is what we call is standard proto, and number two is modified proto. So here are some of the specifications that we referred for both of them, for standard and also for modified proto. Okay, this table shows the difference between standard and modified. Okay, similarly, in both proto tests, the soil is compacted in a mold that has a volume of approximately about 1000 centimeter cube. Okay, with the diameter of the mold is about 4 inch. So the mold used, okay, has the same volume. Okay, neither standard nor modified. Okay, both have the same diameter. Have the same volume. Okay, approximately about 1000 centimeter cube. Okay, 1000 centimeter cube. Okay. So during the laboratory testing, the mold is attached to a base plate at the bottom and to the extension at the top. Okay, so you have this is your mold. This is actually your part of mold, and it has been attached to a base plate. This is your base. Okay, this is your mold. Okay. And you also have the extension here. Here are the extension. Okay, we call it as extension or known as collar. Okay. Okay. The set of apparatus is shown here. Okay, you have also hammer and somewhere else here. Okay. The significant differences between standard and modified proto are the mass of hammer used. Okay, the mass of hammer for standard, the mass of hammer is 2.5 kg. Meanwhile, for modified, you use 4.5 kg. And the fall distance for standard, you use 300 mm. And the fall distance for modified, you use 450 mm. Okay. The rest, okay, it is still similar. It means that in terms of number of blows for each layer, for standard, you are going to compact your soil into 3 layers, while for modified, you are going to compact your soil in 5 layers. But the number of layers for, number of blows for each layer maintains similar for standard and also modified. Okay, so this is your hammer. Okay. What I mean by the fall distance here is this is your hammer. Okay, if you pull your hammer, so the fall distance, okay, so your fall distance is supposed to be straight line lah. Okay, the fall distance here, okay, for standard proto is about 300 mm. Okay, and for modified proto it will be 400 mm. So this is for standard and this is for modified. So if you look at the tables again, okay, you have almost the same, okay, specification, okay, for standard and modified. The difference is in terms of the mass, okay, the difference is in terms of the mass, the fall distance, and also number of layer. The rest are similar. So it can be concluded from here that modified proto test may offers better compaction based on the compaction effort. Okay, why? Because it will be compact, okay, into 5 layers, okay, compared to standard only 3 layers. Okay, you apply the same number of blows for each layer, which means that if you times 5, okay, it will be 25 times 5, 1 to 5, right? So you blows about 1 to 5 to achieve these 5 layers. Meanwhile, for standard proto, if you times 3, 75 only. So you have to blows about 75 times, okay, for everything from first layer to third layer. And you use much heavier hammer, 4.5 kg for modified, as compared to only 2.5 kg for standard. Okay. Compaction tests, based on standard compaction tests, also could not reproduce the densities measured in the field. Okay, maybe. Okay. The aim of the test is to establish the maximum dry density that may be attained for a given soil with an optimal amount of water. So in the end of that, you want to find the density and the water content. So you need to have those relationships, the relationship of dry density and moisture content. So dry density and also moisture content. But initially what you got is the bulk density. Okay, sorry, this is not supposed to be weight because you are using density. This must be mass. Okay, so you're going to get the bulk density. Okay, after compactions and knowing the moisture content, you can calculate the dry density by using these equations. Okay, by using this equation. So as we discussed just now, one point you have to get the bell-shaped curve like this, you might need a series of repetitive compaction procedure. So if you look at you already watched the video just now, that represents only one point. So to get another points, okay, this point, this point, this point, and followed by another points, you have to add what? You need to add the moisture content here. Okay, you increase the moisture content. Let's say initially just now you took 4%. Okay, the next point, let's say you want to add 8%, so additional of 4%. Okay, if you are using the same sample, it means that you remove all the samples from the mold, add another 4%. But if you use the new sample, the new dry sample, which means that the net sample, the net amount of water is 8%. Okay, standard not really recommend that you are reuse back the compacted sample, okay, to be compacted again and again, to be compacted again and again to get points here. But it is just not recommended, but still you can proceed with the procedure. Okay, research might shows that there is an effect on the values, on the results later, but because it's not too significant, it's not affecting the whole result significantly, so you can still reuse back the compacted sample. Okay, why they not suggested? Because when you compact, you already crush, maybe you may crush the individual particle, so that is why they not recommended you to reuse back the sample. Okay, so similarly like previous discussions, okay, you add water up to a certain points of amounts of water. If you add more, then it will not tend to increase the density, but now they are tend to reduce. Okay, remember this is the regions of dry where your dry density increase, and this is the region where your dry density will be reduced. So the separation, okay, is lies on what? On your optimum moisture content. So that's very important for you to know what is the optimal amounts of water to be added in order for you to achieve the maximum dry density. Okay, to achieve the maximum dry density. Okay, and how you want to know whether you already achieved the optimum moisture content, how to estimate. Okay, how to estimate, okay, during testing. Okay, when you compact your soil, let's say you got the total mass, right? After you compact, you weigh the mass of compacted sample. Let's say the first one you got 1750. Okay, and then you do the same, you do the similar procedure, okay, for the net sample with additional water content. So for the number 2 step, you got increase to 1790, and then number 3, let's say you add more water, you got 1860. Suddenly when you add more water, okay, you compare until finish the 3 layers, you find out that it's already reduced 1820. So you can estimate that it increase, and suddenly reduce. So the reduction here, okay, shows that there is an decrease in optimum moisture content later, okay, after being calculated. So you can proceed with maybe sample number 5. Hopefully that it reduced more. Maybe now it reduced to 1796. So it's reduced much more. Okay, so how to know that it wants to stop? Okay, you can estimate. If you can get this nice bell shape, then it's okay to stop the testing. But most likely you're going to repeat the compactions, okay, from one point to another point about 5 or around within 4 to 5 times. Okay, within 4 to 5 times. Okay. Okay, additionally, okay, from that, there's also a line that you have to plot, okay, if necessary, to show you where's the area that has no air at all. Okay, theoretically it has no air at all. If there's no air, means the air void content 0. Okay, corresponding to degree of saturation 100%, because of what? SR is equal to VW divided by VV. If you're talking about SR equal to 1, means that volume of water is equal to volume of void. Means that your void is fully occupied by water, which means has no air. Okay, so theoretically, okay, if this is your line, okay, if this is your line, okay, this is your line, your compaction line, okay, so the air void line would be slightly above your compaction line, okay, which shows that this is the line where there is no air. Okay, and how to calculate that is by using this equation. Okay, if you're talking about zero air void line, means that this one is equal to 0. If you want to find the air void line corresponding to 10% air, okay, associated to 90% degree of saturation, this one would be 0.1. Okay, if you pick 25%, it means that this would be 0.25. Okay, the water content, you are using the same water content. Okay, you are using the same content. If you're talking about this point, or this point, you are talking about its own water content here. Okay, let's consider this example. I have the data based on the compaction test, okay, and standard compaction test. So we have the mass of wet soil 1.791, 1.937, blah 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 until 1.985 kilogram, and it's already given for 1.79 the water content is 84, and the same thing for others, okay, with the respective water content, and the volume of mole using is 0.945 times 10 to the power of -3 meter cube. It's about 945 centimeter cube. The specific gravity is 2.7, and assume that the raw water or density of water used is 1000 kilogram per meter cube. So it's asking you to determine the MDD and OMC. In addition of that, you have to plot the zero air void lines. So before you can get the MDD and OMC, you have to plot the relationship between dry density and also moisture content. Okay, you need to plot the relationship between dry density and also water content. So dry density and water content, or known as moisture content. So you have to plot that. But before that, you already have the moisture content, you already have this one, but you don't have the dry density value. So you need to calculate first the bulk density, okay, equal to total mass divided by total volume. It's given here 1.79, so you have to minus with 0.945, so you get the bulk density for each of the series of data, and then you calculate the dry density, okay, using this equation. So whatever bulk density here, okay, divide by 1 plus water content here, water content for each of them, okay, so you get the value for dry density here. Remember, the water content here, this is 8.4%, so you have to convert into decimal point, okay. So once you already have, okay, now you already have complete, you have the dry density, you have the moisture content, plot into the graph known as compaction curve, okay. So you will have 1 point, 1 point, 1 point, 1 point, 1 point. So you need to plot a best fit curve. Okay, not necessary for you to connect each point. Okay, best fit curve. So it may be like this. Okay, so where's the maximum dry density? Here. So this is your maximum dry density, and this is optimum moisture content. Alright, so finish on that one. Okay, second one, it said that plot the zero air void line. Okay, using the equations provided in the previous slide. Okay, so dry density corresponds to the zero air void line. What is that? So you have the equation here, 1 minus AV, blah, 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 blah. Okay. So you are using the same water content. Okay. But the AV here, you have to minus with 0. Okay. You minus with 0. You calculate the additional from this table. You put the dry density corresponding to zero air void line by using these equations. Okay. The equation that you can refer to the previous slide. So you have another point. Okay, so you will have another points here. So from this point, so maybe you have one here. Okay, the same thing from this point you have and you have here. And remember, this is a line. Okay, this is line, not curve. So you have again best fit line. So you have the line here. Okay, the lines here corresponding to avoid zero avoid line. Okay, so that is my explanation. Okay, to solve this example, what I want you to do is to solve it again. Okay, and consider this is your assignment. Okay, do it again and submit to me later. Okay, with that, let's stop here. Okay, I'll see you back later with the next part, which is third part of this topic. Okay, the third part for under soil compaction. Thank you very much.